So good afternoon and welcome to another AILU webinar. This is webinar number 5, and we're very pleased to have Gwenn Pallier from Cailabs, who is our presenter today. Cailabs are the sponsors of this webinar, and the title is Implementing Beam Shaping in the Laser Industry, Opportunities and Challenges. Just a few words about housekeeping before I hand over to Gwenn. The webinar format means that the participants are not able to speak or to put their video on, but you are able to ask questions using the Q&A button at the bottom of the screen. So if you have some questions, and please reserve this for genuine questions in the Q&A. If they're questions for admin purposes, like I can't hear anything, they won't be answered live. But if they're questions that are relevant to the webinar, then Gwenn will answer them live. We'll group them together and get through as many as we can in the time available. If for any reason we don't get through all the questions, then we will be able to ask Gwenn to answer the questions in a written form and send them on to you afterwards. The webinar is being recorded and it will be available on YouTube and Vimeo next week, and we will send links out to everyone who's registered for the webinar, so they'll be able to see it, and of course you'll be able to find it on YouTube as well. Okay, I think that was all of the housekeeping issues. Just on the timing, Gwenn is going to talk for about 40 minutes, and then that should leave us almost 20 minutes for the Q&A at the end. So without further ado, I'm going to hand over to Gwenn now.
Hi, Dave. Hi, everyone. It's really nice to be here just now. As we were chatting just before, I haven't done a webinar for quite a while now, and I'm quite happy that I have this chance that actually, Dave, you brought me that idea that we could use the AILU platform to talk to everyone about what we are doing at Cailabs. And I wanted to do something a little bit new today. And talk about opportunities and challenges of implementing beam shaping in the industry. That's for me the good part about webinars, is that we are not limited in time as much as we are in conferences, where it's generally 15 minutes of speaking and you are somehow limited in the topics you are addressing. So I'm quite happy that we will have a little bit more time today. And let me now share my screen. Okay, all good. So I'm gonna put it full screen. And I guess I'm sharing the wrong screen if I'm not wrong. Okay, it should be good now. Dave, let me know if it's not. But I guess I'm sharing the good screen.
That's good. Yeah, thank you.
Okay. So this is the topic today, beam shaping in the laser industry, opportunities and challenges. I want to start with a little game about what beam shaping can bring. We have that game when we are kids in France. I guess it's the same all over the world. So anyway, this is still the same image, so you can look at that. So the thing that now with that beam, you can actually have more power and have a more stable beam, because those patterns are more controlled and they don't go to the protective window. And somehow that leads to the image that you have on the left and on the right, which is printing paths. You can one more time see one difference in between both. On the left, you only have cubes on the edge of the building plate, while on the right you have them everywhere. Why that? Well, actually, when you try to print in the middle of the printing area with a high power Gaussian beam, in that case it was 1 kilowatt, there are so many spatters that before you end building your cube, you have actually killed your protective window. So the whole main difference that we want to stress is actually that you can print faster, actually up to 5 times faster, using the appropriate beam when you are doing laser powder bed fusion, which means that somehow you can improve the return on investment of your machine and try to just make more parts per year with the same machine. And just because if we counted well, this is 6. The 7th one is that this is somehow just a beginning. The one on the right is actually much more promising than the one on the left. There is more to come, and by optimizing even better that shape, typically by using M shape instead of ring shape, we can go even faster. So our target is to try to manage to print 10 times faster, but the truth is we have not done it yet. So maybe that's for the next few years. So that's what beam shaping do. It's improving laser processes by using the appropriate beam. So how to do that in the industry? It's what we want to discuss today. So I will be actually quite short on the two first points. I am working at Cailabs, so I will shortly introduce you to Cailabs. Maybe some of you don't know the company yet. I will be also short on the introduction, but I wanted to introduce somehow upscaling the industry in the last 60 years with lasers, and why actually beam shaping is somehow the next upscale that the industry is expecting from the laser side. Still, I want most of the webinar to be on the two following bullet points. The first one is the opportunities. What can we do? What have we demonstrated that we can improve thanks to beam shaping on different processes? And I also want to spend a lot of time on the challenges of those implementation. This is something brand new. This is the first time I present that part. But I think it's quite interesting to discuss what we should pay attention to when we are doing beam shaping at industrial scale. And then I will have a short conclusion on what we are working on now and in the future, and some conclusion. For Cailabs, we do beam shaping. We do that in France for a little bit more than 10 years. We have a lot of application around telecommunications. So aerospace and defense is mostly spacecom, so communication in between the ground and satellite, coding data. And the one on the right in that image is a fiber network. So it's, again, coding data with beam shaping, but inside fibers. But I myself, I only work on industrial laser processing, so making parts, making things, and try to make them better. So it can be a lot of things, your cell phone, your car, your plane. We work on a lot of different applications. Along the year, we actually figured out that there are three main topics on which our technology and our beam shaping solutions are the most relevant. It's welding, microprocessing, and additive manufacturing. And on those three verticals, somehow we can provide you with turnkey solution, but we can also provide you with customized solution to your exact need and exact machine. So this is our building in Rennes. So actually we are, this is not that old. I think it's 2 or 3 years old, but we are already building the next one, which will be even bigger, again in Rennes in the west of France. This is it for Cailabs. Now I want to shortly introduce the story, the introduction of laser processing. So lasers are actually used in so many applications around us. You can maybe have, if you have a super expensive watch on your arm right now, very probably actually part of it is actually manufactured with femtosecond lasers. If you are driving a car, especially an electric car, there are good chances also that there is a lot of lasers involved. The display you are looking at, your cell phone in your pocket, there are lasers everywhere. But also the plane that you may be using for your holidays or business trips. I like the application on jeans. For sure, Cailabs, we don't work at all on jeans, but all those jeans with those fancy images onto them is actually made by lasers or photovoltaic. So really a lot of topics. And somehow, lasers as always unable to provide real upscale to the industry. So it means creating absolutely new objects that would not be possible with lasers, or really upgrading significantly existing objects, or increasing the manufacturing capabilities of existing objects. This is somehow what lasers has brought to the industry in the last decades. Somehow it all started by CO2 laser in the 60s, and CO2 laser were actually just having enough power that you can modify material, that you can actually melt material. So because you could do that, it all started with laser welding and laser cutting. It was already a revolution somehow in the industry, which was somehow pushed a lot at industrial scale by Coherent. It's quite funny to say that somehow beam shaping is already there with CO2 lasers. So we don't talk about that much right now. But actually, they were already doing a donut shape or ring shape using CO2 lasers back in the 90s, just because it was possible. By tuning a little bit differently the laser, you could get a ring shape, and it was actually working fine. With that ring shape, you can already have similar quality using lower power, meaning that you can save money. And funnily, I would say that because back in the 90s, this ring shape was working fine, everybody is always trying the ring shape now because, well, we all know that it's working. But we will see in the next minutes that there is much more to expect from more complex shapes. Somehow in the 80s, another revolution came from a new type of laser being available, solid-state lasers, pushed to them at industrial scale by TRUM somehow, and the beam quality was actually much better, which opens a lot of new application in the industry. Then came the fiber laser, which was quite pushed by IPG, even though there are other brands also providing fiber laser. And the good part about fiber laser is that, well, they are fibered. So the amplification is done inside a fiber, which is somehow much more simple to make the laser, to assemble it, but it's also much more cheaper. So in the end, the lower operating costs of a fiber laser enable to open new application, typically in medical devices or in automotive. Then a bit more than 20 years ago came the ultra-short pulse lasers. That was pushed at industrial scale by the amplitude. And the good point is with those ultra-short pulse is that everything is happening so fast that there is close to no heat affected zone. And this enables actually to process stuff at a really smaller scale and then to actually manage more sensitive materials. So all those were revolutions, and you can see that it was driven somehow by the laser. But somehow, even though there is more and more development in the world of the lasers, shorter pulse, higher quality, new wavelengths, there is a kind of a hard stop right now that it cannot help more the process by itself. You can see if you have more power and you are doing welding, which is happening on the left, it's just poor quality. It is the same actually with laser powder bed fusion. If you are just using the Gaussian beam, you are just actually somehow killing your parts. And it's also the same in microprocessing. You have a very poor quality if you don't change the shape of your beam. And that leads us actually to beam shaping, why it's the next step to improve laser processes. So I want to start by somehow explaining how I will think in the next minutes when we'll be discussing all that. We will be addressing a lot of different applications, but I really want everyone to always think in different steps when we talk about beam shaping. The first question you have to ask yourself is, what do you want to improve? So if you want to do an upscale, what do you want to do? Do you want to process faster? Do you want to process smaller? Do you want to have better roughness on your part? You have to really address one specific topic that you want to improve. Then once you have figured out what is your problem, you can figure out what is the best shape to solve that problem. One very important point that people generally forget is that once you have defined that you need, for example, a triangular shape, it's super important to define what is a good triangle and what is a bad triangle. So criteria are extremely important, and it's really important to know what will make your process being stable and robust when you are using beam shaping. Is it the depth of field? Is it the homogeneity? Is it the precision on the dimension of the shape? All this is actually very important. Once you know what makes your shape a good shape, you can figure out what is the technology which is adapted to your process. And for sure, in the end, cost is coming into the game. Will the price you pay worth the gain you have in your process? So I will really try to go through that and showing that beam shaping can solve a lot of different problems on different applications. But just quickly to say it, it's somehow important, and I will not spend a lot of time on that, but there is more and more beam shaping solution providers on the market. And I would say that globally, I divide beam shaping providers into two big groups. The one who does it inside the laser, the one who does it outside the laser. I help you with the benchmarking. This is somehow who is doing what in that. And I don't have time to debate, even though we have a lot of time, I don't have time to debate what are the advantages and drawbacks of each technologies. For sure, each one has advantages and drawbacks. But what is important for me as a message is, if you want to define what makes a shape a good shape and having the right criteria, for sure, two squares made by two different technologies will behave differently. So it's really important to not compare carrot and apples and to be careful when you are comparing shapes made by different technologies. What we do as Cailabs is multiplane light conversion. So the idea is that we started with that brick that you see on the left. It's an image which is 10 years old or something like that. The idea is that we can do any kind of intensity profile, and we can actually control as well the phase profile through a beam shaping with a lot of different phase plates, one after the other. All that is based on mode propagation, so it's not based on diffraction. It's really made on calculated by propagating the different modes of the laser. And as you can see, it's fully passive and reflective, which is really good if you want to manage high energy, high power, and preserve typically the spectrum of short pulses. When you implement that for laser processing, it gives the system that you have on the right. It's actually implemented in between the laser and the process. It can be fibered or free space, and it's important to say that it's compatible with all lasers. When we implement that globally, there are two ways to do it. One which is inside the machine, so you have the laser. Generally, then you adapt the beam to the beam shaper.
Gwenn, sorry, we're getting that interference again on your voice. Maybe you can mute the videos, or I don't know if there's any sound in the background of the videos, but
maybe no. Yes, they don't move, which is good. So you don't see the rays going anyway, never mind, but that's the implementation in the machine. So then you have the beam shaping box, and then you are going through a scanner typically. But we also have implementation into laser heads, like this automated fiber placement or laser welding heads. I believe that you all know that graphics just now. It's graphics which I loved when I discovered it a few years ago. It's telling you what laser you should use depending on what process you should do. And I actually believe that one day we will have the same kind of graphics telling you what beam shaping technology you should use based on what process you want to do. Still, I want to say that we are actually providing solutions which can go from monomode to diode laser, so all kind of lasers, CW to ultra-short pulse, and UV to CO2. Now, let's try to discuss a little bit what are the opportunities that beam shaping can bring for different processes. So I will be focusing on really explaining why one shape is helping to solve one problem. So I'm not going to read all the details of the process because somehow it's not what I want to stress. Nevertheless, everything is written on the slide, so you can read them. And on the left, the next slide will be always organized in the same way. On the left, you have the name of the process with some image of the process. And on the right, you have the shape that we were using. Then we will discuss what actually we demonstrated in terms of gain and why it's a real opportunity for the industry, a real upscale for our customers. So I want to start somehow by, I would say, our most important topic, microprocessing. And it's, again, the most important slide among all of them is probably that one. It's about mode cleaning. So mode cleaning is a unique feature that enables to transform, wait for it, a Gaussian beam into another Gaussian beam, and we call that beam shaping. Because that Gaussian beam out of our module is actually extremely stable. The idea is to do passive stabilization. So even though the beam at the entrance of the system is shifting, is tilting, is elliptical, astigmatic, the output of our system is always the same, not moving, and having the same shape. This has a cost transmission, but it can have a lot of advantages. Typically, in that case, the fact that it's extremely stable enables to have a much more robust fiber launching. So it means coupling into a hollow core fiber. Why that? When you do active stabilization, if the laser is moving too fast, actually, sometimes it's not following, and it's damaging the fiber, which you don't want to happen. In our cases, if the beam is really moving too fast, you just lose transmission. So in the end, you just don't have power going inside the fiber. This enables actually to have a depointing, which is divided by 16, making actually the femtosecond fiber delivery much more industrial, even at high power. But we have also done beam splitting, so I guess it's quite obvious you do parallel processing. What is maybe funny to say is that even though we have 5 beams, the process space is only increased by a factor of 2.5. This is due to the scanning time. Of course, you waste a little bit of time during the round all around the part. But nevertheless, the bigger the parts, the closer to 5 we would be. And this is important to improve the return on investment of machines. But a funny one is that you can do somehow exactly the same, not by splitting the beam, but by shaping it. So let's imagine that you want to drill something which is really having a square shape, a riblet of the square shape. If you want to do it with a Gaussian beam, you have to have a very small Gaussian beam, and you have to go multiple times inside that square drill that you want to have. If you have the right top hat, which is very sharp of the right size, and you put more energy into it, you can actually avoid this lateral passes and have just one of it. And globally, you can improve your process speed by a factor of 17. So again, the idea is to increase the speed and try to get to the targets of the industry in terms of process speed. But by shaping the beam, you can also just increase the precision. So typically, we are again trying to drill riblets, but in that case, they have a triangular shape, and you want to be able to position exactly where is the bottom part of this drill. If you do that with a triangle and you are somehow scanning parallel to one side of the triangle, you will have your maximum depth on the edge. And if you rotate your triangle and you are actually drilling perpendicular to one side of the triangle, you will have your maximum depth in the middle. So by tuning that, you can actually increase a lot the precision you have in the positioning of your maximum depth. And this is actually super important to create new products. This is it for microprocessing. I want to mention also some improvement that we can do on laser welding. I will be somehow focusing a lot on this ring dot shape of ours, even though we are investigating some more shapes. This is the one we have actually tested the most, and it's actually providing a lot of improvement when it comes to copper welding. So we did work on hairpins welding, and the idea was to work with a lot of soiled samples, misaligned or with fingerprints and stuff like that. And in all cases, what we demonstrated is that by shaping the beam, you can actually reduce a lot the spatters because you are stabilizing the med pool. So we divided the spatters by a factor of 2, which was important to decrease the scrap rate. But we also worked on bus bars. In the case of bus bars, we were actually more focused on simplifying the fixtures. So the fixtures for holding those bus bar are not that easy to make. And in our case, we wanted to try to weld with gaps. And again, we stabilize the melt pool with the beam shape. And doing that, we are able to have a 1.5 times larger gap compared to no beam shaping when it comes to bus bar welding. So this is really important to enable to have a more flexible production. Of course, when you do immobility applications, you want to do cell contacting. So in that case, the whole point was to remove wobbling. So it's possible to weld those batteries using a standard beam, but what you're doing is that you are actually doing a lot of little circles in order to control your melt pool and in order to have compliant welds. And what we wanted to do is actually we wanted to remove wobbling. So for sure, you are changing all the process parameters, but what is really important to notice is that where globally, by removing the wobbling, you can globally increase the process speed by a factor of 5 because you don't have to do all those little circles. And this is quite important if you want to, again, improve your manufacturing yield. One last one, which, to be honest, was a little bit surprising for us, is when you're doing a welding of copper, what is globally difficult is to go very fast or to go very slow, because in both cases, the melt pool is not that stable. And if you want to weld deep, and you have a fixed power, you don't want to use more than 8 kilowatt, for example, actually you have to go super slow, 3 meters per minute. And not only it's not possible to do that without beam shaping, but even the other state-of-the-art technologies to do this kind of welding were also not stable at that low speed. And somehow we managed to do it. So at similar power, 8 kilowatt, we managed to weld 1.5 times deeper compared to no beam shaping, which was a good improvement. And why it's important, the idea behind is that with the same system, you can actually weld a lot of different parts. You can weld deep, you can weld null deep, and all that you are doing that with the same laser and with the same head. And this is really important because we have to go to flexible production because right now the world of EV is changing pretty fast. It's not like 10 years ago when you have one production line that will make the same cars for the next 10 years. Now the cars are changing every year somehow, and you have to be able to reconfigure your production line. This is it for laser welding. I will be very short on surface treatment because in the end, it's not a big business for us. But I wanted to mention at least that specific use case, which is somehow quite important because we were really comparing the performance with diffractive optical elements, so with a competitive technology. So in that case, we really tried to optimize having a square with a fixed setup. The square was 1 millimeter by 1 millimeter. And our customer really needed to have a high depth of field because they are processing very large parts and they do that very fast and those parts are not so precise. So if your depth of field is too small, somehow it's impossible to have this roll-to-roll process. And at the same time, since they want to really go fast, they want all the energy which is in the laser pulse to be useful. So we were really calculating how efficient, how much of the energy is really efficient to the process. And we managed to actually have a depth of field 4 times larger and at the same time a better efficiency compared to other technologies. The whole idea is actually only by doing something at the same time very tolerant and very efficient, you can really implement this process, this laser process in the industry to replace non-laser process. In the case of cutting, it's also not a big business for us, but we did work at least on one project with this C-dot shape. And the whole idea is to actually cut very thick parts, but having the same energy all along the curve, which is not the case when you are using a standard Gaussian beam. So when you manage to optimize the energy all along the cutting curve, somehow what you can do is that you can remove post-processing. And it's super important because the whole idea is that you're cutting those parts because you want to weld them after. And if you can avoid the pre-processing application, you are saving a lot of time. So beam shaping, in order to optimize the energy through a 30 millimeter stainless steel cutting application. Additive manufacturing, it's actually a super hot topic for us as well, and we work on a lot of different applications inside additive manufacturing. I will mention somehow each of them. The first one is automated fiber placement. So you have a big mold and you are actually applying a fiber onto that mold, and you want with beam shaping to have a very homogeneous heating of that fiber. And what we did demonstrate is that using our reflective technology, we managed to develop a solution which is 2.5 times more compact. So this is also something that we can do, make heads which are more compact in order to process in more constrained spaces, for example. And in that case, the idea is to go to get into more curved molds. So, and that enables actually to print new parts for our customer. We also work on laser polar bed fusion. So in that case, we want to process, and I know that Inconel 939 is not unprocessable. It's just that with that specific machine we were using, it was not working at 200 watts. And somehow by optimizing the thermal profile seen by the powder, we managed to reduce hot cracking and to print one new material with a similar machine. So printing new parts with old machines. But the big stuff in LPBF is process speed. So we did also demonstrate that using this ring shape, when we are doing the process, we can increase the speed by a factor of 3.3 in the case of this shape. And as I said, we did go up to 5 with some other shapes. The idea is actually to improve the return on investment and to open new markets. Because right now, the fact that the machine is somehow a little expensive and that you are limited in the number of parts you are making, it's also limiting the markets it's addressing. So it's mostly used for aerospace. And the whole idea of printing faster is actually maybe to go to automotive and to find a new application to LPBF. And that's a new topic. We started to work actually on a wire. We have a European project on a wire DD. The last laser processes which was missing, maybe at least in IR on our side. So the idea is actually to, again, with our beam shaping technology and reflective implementation of it, to make a smaller head, so like really smaller, and to also manage more power, which should enable to print new material. So in that case, to be honest, we have not printed anything yet. So stay tuned, and hopefully next year we will present some results on that. So I think I've been through the different opportunities linked to beam shaping in the industry. Now I want to discuss also the challenges, because doing all that, having all those results, to be honest, was not that easy. And I want to at least let you know a little bit about what you have to expect and what is important to pay attention to when you want to implement beam shaping in the industry. I will focus on our 3 main applications, because the truth is we don't really make so much business in cutting and in surface treatment. Therefore, I cannot talk much about the challenges of the implementation. And let's start with laser welding. Well, for me, the biggest challenge was managing all those different lasers. So it's somehow impossible that with the same beam shaping optics, you can manage monomode laser, disc laser, and highly multimode like diode laser. And that's somehow complicated to explain, that when the lasers are behaving so differently with so different BPP, it's actually difficult that the same beam shaping optics is working for all of them. So somehow we managed to have some designs which are compatible with a range of lasers, but it's a real challenge that so many different lasers are available in the industry, especially at the R&D stage in the academy, because once you go to production, somehow this is settled because it's generally 10 times or 100 times the same laser, and that's somehow figuring out, solving the problem. And it's important to know that even though the system is compatible, because I would say that our beam shaping systems will be compatible of a lot of different lasers, still, if you really change the laser a lot, like you go from a 50 micron fiber to a 200 micron fiber, it will change the shape. And that's also something which is not so easy to manage, because you demonstrate something with one laser, and if you want to do exactly the same stuff with another laser, actually it's not sometimes possible, because you will not have the same shape somehow. It's possible to design systems which are more robust to input variation, but now the challenge is that you have to find the right trade-off, because if you want to have something which is much more robust to having a lot of different inputs and providing the same shape, somehow you have to degrade the quality of the shape you are targeting. And by degrading, I mean that you cannot make as small a shape as if you target to have one system for one type of laser. So that's somehow one of the big challenges that we have to address to further use beam shaping in the industry. The other challenge I see in welding is that there are so many different applications. So I did mention this 4 application on copper, and we were very happy that we did that. And then actually, when we tried to get to the industry, we realized that everyone is having his specific way to implement it. And the question is it one problem, one beam shape? I think it's not the case. Hopefully it's not the case, because it's not somehow easy otherwise. But nevertheless, still you have to figure out, still in a range of shapes that are available, what is the one solving your problem. And the thing that a lot of things can change from one application to another. You try to solve a different problem. Is it gap? Is it speed? Is it pores? Is it spatters? Is it hot cracking? So depending on what you want to solve, for sure, you need a different thermal profile. Then the material references, especially when it comes to aluminum, every aluminum is so different one to the other. Welding configuration, obviously, if you want to weld parts one next to the other or one top of the other, it's super different. All the fixtures, the laser, as we discussed, and the optics. Still, right now, the conclusion is that with a few shapes, all those shapes that you have on the right, we did them already. So we are welding with those shapes. And with that range of shape, you can actually solve most of the problems of laser welding. So you just have to figure out which one is the one for your problem. And how do you do that? Sure, you have to do process development. I guess it's still the main step, and that people only believe things that.
Gwenn, the sound's gone again, so you probably pause the video.
This is a cool video. Never mind. Yes, thank you for reminding me that I cannot have videos. So this is process simulation. So it's a nice video of how to simulate the process. So if you don't want to always develop the process, if you don't want to develop weeks and weeks of process using different shapes, for sure there is a way through simulation. And at Cailabs, we're working a lot on that. We work with the University of Vienna on figuring out what are the good shape at the simulation stage. And you can see that it's actually super exciting to do it, and you can really be super creative in the shape that you're testing. And we develop a way to score the performance of each shape to figure out which one is actually the one giving the best performance. So this is for laser welding. Actually implementing beam shaping in microprocessing, I would say, is even more challenging. So there is a lot of things that you have to pay attention to. And the first one is actually the instability in the input beam. So the laser, when you are sometimes changing the parameters, can change. It depends on the laser brands, to be honest. But even though the laser is extremely stable, still the whole environment will be somehow super sensitive to any thermal change that you may have, especially at R&D stage when you are not inside fixed machines. And whenever your beam are moving, it's extremely difficult to do beam shaping. So I'm going back to my mode cleaning feature, and this is how we solve that problem. So whenever we do beam shaping on free space moldable laser, we do actually passive stabilization before. So we have this mode cleaning, which is providing a very stable shape, and then we shape it, and then it enables us to always preserve the beam shape. What you're seeing here is that when you're shifting the beam from left to right, using MPLC, so it means that passive stabilization plus beam shaping, or just doing beam shaping, typically using a DOE, you have a very different shape behavior. So in our case, the shape is fully preserved in the processing plane, but the transmission may change a little. In the case of a DOE, you can see that the shape will change a lot when the input beam is actually moving. Another challenge, which is somehow linked also to the laser, is the size of the part that you want to dimension. So you all know that the rayleigh range is actually proportional to the square of the size of the beam. So when it goes to very small beam, it's a little bit catastrophic. So if you go to a beam which is 10 micron, actually in the end the rayleigh range is 80 microns, so extremely small, not industrial at all, and that makes it super challenging somehow. And the thing is, if you don't pay attention to the plane, to the face of your shape beam, you can really have, in the end, depth of field which is way smaller compared to the Gaussian beam. So in our opinion, the conclusion we had at Cailabs is that somehow you cannot only shape the intensity profile, you have to shape also the phase profile. So to do that, you need to have at least two planes. And in this example, we demonstrate what's happening when you have the same square at focus, but you do beam shaping using just one plane, so typically using one diffractive optical element. Well, you can see that at 10% of the rayleigh range, your shape is already killed. So 10% of 80 micron is actually 8 micron. So it means that you end up with a depth of field which is extremely small. And if you manage to preserve the face, to have a plano face at the point where you have your beam shaping, you can actually have a way larger depth of field for your shape beam. So you need to pay attention to the instabilities, you need to pay attention to the depth of field, but another super challenging point is paying attention to the optical setup. To be pretty honest, having a nice shape beam at the output of our module is not so difficult. What is super challenging is to have that same nice shape in the processing plane, going through the scanner and going through the F theta. So in that case, it's just simulation, and it's not taking into account at all any way to do beam shaping. It's just pure estimation of the cropping of a scanner and an F theta. So in that case, we make a 20 micron beam or a 50 micron square beam, and we are using a 20 millimeter scanner, so pretty standard, and 100 millimeter F theta lens at 1 micron. And what you can see is that if your input beam is having a sharpness of 0.1, so meaning that the transition is 10% the length of the plateau, it's when you are actually doing a very small beam, it's just cropping. It's cropping everywhere, and you cannot preserve that sharpness. So not only you cannot preserve the sharpness, but the thing is that it's actually destroying the shape. So it's super important to really pay attention to having the proper numerical aperture, depending on the size you want to have in your processing plane and depending on the optics you have on the optical path. So this is another example, and in that case, we just change one thing. We change the focal length of the F theta. So we go for a shorter F theta, meaning it's having a higher numerical aperture, and you can see it's way better. So you can, in that case, preserve the sharpness even of a sharp beam. When it's 50 micron, it's perfectly preserved, and it's actually not that bad when you're looking for a 20 micron beam. And then in that case, we go back to the first setup, 20 millimeter scanner and 100 millimeter F theta, but we change the sharpness. So if we start with a beam which is a little bit smoother, it's actually not cropping, and you manage to preserve a nice beam shape up to your processing plane. And actually, you can see that it's not that bad even at smaller scale. So the message here is it's not always the sharper the better. Yes, in principle, the sharper the better, but the thing that you have to make sure that you can preserve your sharpness through your whole setup up to the processing plane, which is thing that we are always paying attention to at Cailabs. Last point regarding microprocessing is finding the right trade-off in between sharpness and depth of field. So the sharper the beam, actually, the smaller the depth of field. So then again, we need to discuss a little bit on if you want to have something sharper, are you sure you can manage the smaller depth of field of your beam? So additive manufacturing, it's shorter to discuss the challenge of implementation of additive manufacturing. I just want to actually mention that one point. which is the fact that you want to have a small Gaussian beam and a large ring. If you want to print faster, you want to have the small Gaussian beam to print your contour, and you want to have the large ring to print the inside part. And you cannot have that with double core fiber laser. Once your core diameter is fixed, your ring diameter is fixed as well. But more flexible beam shaping technology enables that. And typically, we have developed systems that you can switch in between different shapes, and you can switch super fast in between Gaussian, whatever ring you want, or whatever top hat or M shape you want. So I have a video. I will not speak when it's running, so you can see that a little bit. It's a lab demonstration. So you can see. Okay, so for those attending Munich next week, we will have a live demo of that. This is what we are working on in order to enable a very fast switch in between a Gaussian beam and a large shape. So it doesn't have to only be the exact shape, but it also has to be extremely fast and extremely precise, which is not that simple in the end. So those are the biggest challenge that we have to face when we develop systems for laser powder bed fusion, having the right shape and being able to switch fast. What's next? I will be super short on that. But the thing is that it's not me saying it. This is Rudolf Weber. There will be much more power in the future, apparently gigawatt CW and 100 kilowatt femtosecond within 10 years. And at that power, beam shaping is definitely not an option. So beam shaping is going to be more and more important in the future. And at Cailabs, we are working on a lot of stuff. We are working on having systems compatible with more power. We are also working on combining functions. We will have a live demo of that also next week in Munich. We work on having dynamic system. You saw it just before, lower wavelengths, more complex shapes, and new application. To do that, we have a lot of projects. So some on microprocessing, on welding, and on additive. So again, follow us, and in the next few years, you will see all those results. So I'm reaching now the conclusion of this webinar. So I guess that we did say it, there are a lot of opportunities and a lot of things that you can improve with beam shaping. So now I'm really happy to hear the different problems that you would like to tackle with beam shaping. It's really important to start by well defining the problem you want to solve. I did say it also, I don't want people to compare apples and carrots, and because people complain that apparently we should not say carrot and apples. Apparently we should say apple and pear, so don't compare apple and pears either. And actually, where I come from, in the west of France, in Bretagne, we say that you should not compare les choux et les carottes. So different technology means that in the end, you can have different process results. Please think out of the box. There are a lot of beam shapes possible. And I think that this is really the beginning of beam shaping and how we can improve things with beam shaping. I'm concluding by saying that Cailabs is a super cool company in a super cool part of France, and we are hiring. So don't hesitate to reach us also if you are looking for a job. And I was a little bit long, but this is the end of my presentation about opportunities and challenges of beam shaping in the industry.
Thanks very much, Gwen. That's excellent explanation of beam shaping. And now it's time for people to ask questions. We have one already asked about halfway through, so it may have been answered by what you said at the end. But the question is from Juan Carlos Pereira. Do you see any advantage or benefits in using beam shaping in DED-LB, laser beam powder metal AM, or for repair depositing metals?
It's an excellent question, and it's quite, for me, surprising that there is not more investigation in the academy on those topics. Because if beam shaping is useful for laser welding and laser powder bed fusion, for sure it's also useful for DED. So actually, there is beam shaping in wire DED for years now. There is a solution from Precitech, which is called coax printer. So it's a ring with a wire in the middle. So this is, I think, one of the most successful implementation of beam shaping in the industry. And it's pretty clear what it's providing. You have the same behavior of your process, no matter the direction. Nevertheless, I believe that we can do more, even in the future with wire DED by typically looking at more complex shape than a ring. And I'm quite sure that within this REPAM project that we have, and actually Prestec is also part of the project, we are investigating that. On the powder side, we will also work on that inside this REPAM project. And I'm super sure that, again, you can stabilize things quite a lot with beam shaping, but the truth is I have never seen any results. So hopefully I would say that within maybe 6 months, we will have our first results at the front of AWS. So hopefully we will be able to discuss about that next year.
Excellent, thank you. Next question from Cameron Pullum at Manchester University. Hi Gwenn, thank you for your presentation. Do you face any issues with thermal lensing in high power applications, given the shorter depth of field?
Yes, it's super important. It's super essential. So I don't know if he's mentioning somehow what process he's mentioning, because the problem is not the same with all process. On welding, typically, no, not really. We have pretty stable in the end system, so it's not so much of a problem. But in microprocessing and in LPBF, it's super important. Typically, the collimator, which is in front of the fiber laser in LPBF, they definitely have thermal lensing. So the thing is that it may not be so much of a problem as long as you don't do beam shaping, but as soon as you do beam shaping, it's becoming a problem. So we have to pay attention to that. And our solution in the end is to look at the whole optical chain. In microprocessing, we end up advising all optics on the optical path, because we know that some glasses have more or less thermal lensing. And if you don't use the high quality lenses, it's just moving too much and it's just not stable in the end.
Okay, thank you. Yanis Metzios, what is the biggest aspect ratio that you've achieved in a linear beam using the various technologies at Cailabs?
Aspect ratio could be in 2 dimensions. So, but I would expect it's making a line. My understanding.
So.
Yeah. It could be actually in along the focus. We also do 3D beams, but I expect it's in line. And we did 1:20. So the length is 20 times the width of the beam.
He's clarified. He means along the line. So yeah, that's it.
Yeah. So I would say that it's not a limit. It's just that nobody asked for more than that up to now. And to be honest, most of our demands are not for lines. In the beginning, we were thinking lines would be a huge success. And in the end, most people are happy with a run on a square top hat. So if he has something specific in mind, I'm happy to discuss. And I guess it's not a limit. Nevertheless, the longer the aspect ratio, the more we may have difficulties to avoid distortions through the F theta and this kind of stuff of the beam.
Yeah. Okay. So Tin Brudnick says, very nice presentation. What is your favorite beam shape?
What is my favorite beam shape? Well, the coolest we did is a 3D shape, but it's confidential, so I cannot display it. But it's getting really exciting when it comes to really shaping not only one point, but really in 3 dimensions. That's really super exciting. And it's super difficult to measure it, because you don't have to put the camera just at the right place and measure it. You have to actually scan with your camera, be sure that when you're scanning with your camera, actually it's scanning without any misalignment or anything. But when you manage to do it, it's really cool.
Yeah. Okay. So Shahid Jabbar says, how customizable are the beam shapes? Capability of creating different shapes using the MPLC device? So
we are mostly known for static shapes, which is for very simple. We are mostly providing static shapes. So it's one system, one shape, basically. In LPBF, there is no market for that. So it's one shape plus a bypass. In microprocessing, we are launching in Munich also a new version of the module with one shape and one bypass. So you can have the Gaussian or top hat. And it's quite easy to customize your shape. So typically doing a triangle instead of a round is not so complicated. Generally, the devil hides in the details, we say in French, meaning that the shape you can achieve depends not only on our capacities, but also on your whole setup. If your laser typically is a little bit creepy, we cannot make miracles with that. If you have a very small numerical aperture, we cannot make very small shapes, so there are limits on that. Then when it comes to changing shape and trying a lot of shapes, I would say that it's under development. So for now, it's R&D stage. We tried that with a few academics. We tried that in the lab, but it's not available as an off-the-shelf product yet. And it's not going to be available, I guess, this year. So hopefully next year.
Okay, excellent. Marcus Kogel-Honecker asks, how much lab work can be saved by simulation from TU Vienna? And how do you see the future importance of modeling, not only in welding?
It's a really cool question. So the first time you work with Andreas Soto, you lose a lot of time compared to doing the same in the lab, because you have to fine tune and understand all the way the simulation works. So the first time was much longer than we thought. And when we do it the second time, I would say that it's actually more or less the same time as process development. And I expect that actually it's going to be just faster and faster. So yes, in the end, you save time, that's for sure. You have to be sure that you understand well how the model is working. Typically, the way they were modeling the rays, how they attack the material, was not matching by the way actually the rays are behaving using our technology. So we had to adjust that with them, and it took some time. And the future is it's going to be more and more important, I expect, because it's faster, it's cheaper for sure, more flexible. So it's probably also more environmental friendly, because you don't make one hardware just to test some stuff. You don't waste material and anything. And with the use of artificial intelligence, it's going to get just better and better. So they have a whole roadmap using AI. First, they want to use AI in order to faster get the results, like typically counting pores in the simulation and stuff like that. Then they want to use AI to extrapolate data. So they do welding at 3 meters per minute, welding at 6 meters per minute, and they want to know what's happening at 4.5. Then they use AI to do that. And then they want to use actually AI maybe to improve the equation they are using to do the simulation. So they use some specific equation right now, and they expect that they are better ones. And they say that the ultimate goal is actually that you will open ChatGPT and say, oh, I want to weld a bus bar for this battery application. What shape should I use? And ChatGPT will answer what shape you should use. But for now, that's a little bit of science fiction, I think.
Yeah. Okay, good. So Rashad Bakhtari asks a couple of questions. Can the orientation of beam shape be aligned to the welding path, like using a non-asymmetric axisymmetric beam for a circular welding path with the MPLC technology?
So yeah, that's the excellent question. If you do an asymmetric beam and you don't rotate it, I would say that basically it's pointless. So before making it a real product, we want to be sure that asymmetric beams are really useful. And we are investigating that right now. So typically, we have a lot of work which is done by the FSW on the topic. And they demonstrated that asymmetric beam is useful. So now if it's really useful, we have to rotate it. So there are many ways to do it, which is not so difficult. Typically, the guys at the FSW, they find their own way to rotate it the hard way, a little bit dirty way maybe, but it works. I would say that we will have to find an industrial way to do it, and probably the way to do it will be somehow, again, using 3D shapes. So one way to have one thing we can do with 3D shapes is that along the focus, the shape is actually rotating somehow. And then by just defocusing, you are actually rotating your beam. This is the kind of stuff that we are working on at Cailabs.
Okay, good. And another question from the same person. What are the challenges of simulating the beam shaping in applications like welding and LPBF?
So what are the challenges? I would say that maybe the question is not for me. Maybe, first of all, you should ask that question to the guys doing the simulation. But from what I saw, it's not so easy somehow to simulate really the way the ray propagates. So they are not going straight to the material. They have their propagation way and all that. So it's a little bit complicated. Then I know that they struggle with exactly the same as with real process development. If you use copper ATP or some other copper reference, it's not giving the same results. And if you just change a little bit whatever your the material, how it's made, it's also not giving so much of the same results. Nevertheless, I would say that right now on welding and on LPBF, it's quite solved. And even in femtosecond, it's actually getting better and better. So because nobody was simulating beam shaping in microprocessing, we started to do it on our own. So if you are motivated, I think it's something like 8:30 Monday morning. One of my colleagues will be presenting at LIM in Munich some results of simulation of beam shaping for microprocessing.
Excellent. Okay. Yeah, it's worth pointing out at this point, we have an AILU webinar from Flow 3D about simulation and CFD and modeling laser welding in particular. So
yeah, it's an excellent software, Flow 3D. They do really cool stuff, and it's easy to use.
Yeah. Okay. So I think that's the last of the questions at the moment. I have one question for you, Gwenn. You mentioned that right at the end of your presentation about the power levels going up and up in fiber lasers. As we've seen, we're already up to sort of hundreds of kilowatts, and potentially we might be the roadmap might be going even higher. Where is the limitation, do you think, for the MPLC?
So right now, it really depends on the laser. So when it comes to monomode laser, it's much more difficult to do beam shaping. And in LPBF and in microprocessing, it's monomode laser. So every time we increase the power, sometimes it's a little bit challenging. When it comes to welding, nothing afraids us. So if you have a 100 kilowatt laser and you want to do beam shaping, and if it's not monomode, I would say we can go for it. We just make the system maybe a little bit bigger, but it's not so difficult to do it. And cooling down and all that is not so difficult. The problem of monomode laser is that any movement of the beam is actually killing the shape, which is not the case with multimode lasers.
Okay, excellent. Thank you. Okay, so it's 2:59 here in the UK, 3:59 over there. So I think there's no open questions left. Oh, maybe a last one. Okay. They're coming in now thick and fast. Okay. Okay, so Nicholas Dallos says, you've mentioned that for process development, trying different beam shapes can take weeks. Have you tried any algorithmic approach to reduce this time?
No, we did not, and it's interesting because I saw that there are some studies right now to try to implement that. Typically at the FSW, I also saw that they were working on that. I guess that we are still at the step that in the end, for now, you don't really save time, but the next time you're going to really save time doing that. So probably we should work on that as well. But right now we are quite systemic, and we use a very famous intelligence, the human intelligence, to figure out how to pick up the right parameters.
Yeah. Okay, so let's have one last question, which is on the screen. What is the best way to isolate the effect of beam shape in LPBF, as Gaussian and ring beams have different spot sizes and energy distributions?
It's just impossible. So at least what we did is we tried to compare Gaussian and a ring of the same size. And you cannot imagine how many times people came to me and said, "Oh, marvelous, at least you are comparing beams of the same size." Yeah, but define the size. It's anyway not the same size, because how do you measure the size of those beams? So it's a philosophical debate. So no, you cannot really compare. I would say that anyway, for me, my opinion is that in the end, you should optimize one and optimize the other. And anyway, there is an optimal in both cases, and compare both optimals. Yeah. But for sure, it's the carrot and apples topic.
Yeah. Okay. Right. Well, we've come over the hour just, so I think it's time to say thank you very much, Gwenn, for presenting and answering all the questions, answering every question, which is excellent.